Hi, my name is Eliza Simondera, and this is my lab report for the second lab, Projectile Motion. The purpose of this lab was to compare the observed and predicted position and velocity graphs as a ping pong ball was thrown. With that being said, the system was a ping pong ball and the surroundings were everything else, including gravity and air resistance. The concepts that were applied in this lab were Newton's second law of motion, which states that the acceleration of an object is directly proportional to the net force acting upon it, and inversely proportional to its mass. Gravitational force, which is the force exerted between two objects, pulling them together, and drag force, which is the force exerted on a moving object by surrounding fluid, which in this case is air. The equations used were the gravity force formula, the velocity update formula, the position update formula, and the drag force formula. The experiment was set up by laying down a meter stick, which is necessary for the tracking software as it acts as a calibration stick. We then threw the ping pong ball from one person to the other, recording as it flew through the air. I then uploaded the video into the tracker software. Once it was calibrated and the axes were set up, I tracked its position frame by frame. This resulted in data that I graphed in Excel. I then used GlowScript to create two projected graphs with the formulas, one with drag and one without. I used trial and error to find the drag constant. To analyze the results, I combined the three graphs and observed the differences. This is the video that we recorded of the ping pong ball being thrown. This is a screenshot of the tracker software that was used to create the position and velocity graphs. As you can see, the meter stick is being used as a calibration stick, and the purple lines are the axes, which were placed where the ping pong ball started. The red diamonds following the ball's paths are the position points. They were recorded frame by frame as the ping pong ball flew to the other person. As you can see on the right, the graph was made in the software and the data points are all below. After tracking the marker in the tracker software, I copied the data to Excel and created this graph. Because the video was recorded backwards, I flipped the sign of the x values so that the graph would be positive. The line is the same that it would have been if the points were still negative. As you can see, the graph of the x position versus time is almost a straight line, while the graph of the y position versus time is more of a parabola. The points get a little wonky at the end because that is when the ping pong ball was caught. This is the GlowScript code. The highlighted boxes are lines that I changed. First, I set the mass to 0.0027 kilograms, as this is the mass of the ping pong ball. I then set the ball's initial position to 0. I found its initial velocity by finding the average velocity between the first two frames of the video. I set the initial time to 1.45 seconds, as this was when the ball was thrown in the video, and set the final time to 2 seconds, as this is when the video ends. I set the net force to be equal to the force of gravity plus the force of drag, as these were the two forces acting upon the ball. I added the velocity and position update formulas so that the position would update in each time step. I finally set each arrow to a vector so that we could see where gravity and drag were pointing. I ran the code and this was the model that was projected. The images on the left are the actual models of the ping pong ball being thrown. The blue arrow represents the force of gravity, and the orange arrow represents the force of drag. The graphs on the right are the predicted position graphs. As you can see, both graphs are curves, but the bottom graph, which includes drag, is much steeper. When I combined the three graphs, I noticed a large difference between the predicted path without drag and the other two. The ball goes a lot higher and farther. The predicted path with drag is slower, which is why it doesn't make it as far as the observed path, even though they hit around the same height. Discrepancies in the three paths can be noted to multiple things. First is the drag proportionality constant. This number was found through trial and error, not calculated, which means that it may not be accurate and the predicted path could be wrong. There was also probably human error in the experiment. First, we had to throw the ball, which may not be super accurate if the ball went sideways at all. This is an issue because it is introducing another coordinate in the position that we did not account for. Another error is that the video was hand-tracked, which could lead to some errors in the position points. Our first discussion question is to determine if any of the models predict a terminal velocity, which is what happens when a free-falling object experiences no net force. I determined that the model with drag does predict a terminal velocity, as the slope is decreasing and eventually will be 0. Our second question imagines if the object of the ball was thrown straight up instead of forward. With this new path, the ball would take longer to reach the starting position as it wouldn't have to move along the x-axis. Because of this, it would go higher and take longer to fall. We can see this with the two equations below. The equation on the left is the time it would take the ball if it was thrown straight up, while the equation on the right is if the ball was thrown like the experiment. The only time these two equations would equal is if theta was 1, which would mean that the ball was being thrown straight up.